Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be exploring the fascinating hidden world of animal intelligence. For a long time, people measured intelligence by how closely another mind resembled our own. But nature has been solving problems in many different ways for far longer than humans have been asking questions. An animal does not need human language to reveal thought. It may show memory through a journey. It may show planning through a hidden meal. It may show understanding through a glance. Across the living world, minds have evolved to fit the lives they serve. Some are built for cooperation. Some are shaped by danger. Some reveal abilities that still surprise the scientists who study them. The more closely we look, the harder it becomes to draw a simple line between instinct and intelligence. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, there's nothing you need to do but relax. Let your shoulders soften. Allow your breathing to slow. And as your mind begins to loosen its grip on the day, join me as we explore the hidden brilliance of animal minds together. Let's begin. Crows can solve puzzles that challenge many young children. In laboratory tests, these birds have faced boxes with several moving parts that must be handled in the right order. A crow might need to pull a string, slide a door, remove a peg, and use one object to reach another before any food appears. What makes this astonishing is not just that the bird succeeds. It is the way it pauses, watches, adjusts, and then tries a new approach when the first one fails. That looks very different from simple trial and error. It suggests a mind that can hold a goal in place while working through separate steps. Some species can even remember a difficult solution after time has passed. In the wild, that kind of flexible thinking helps them deal with changing streets, strange objects, and unpredictable people. A crow on a rooftop may seem ordinary, but behind those dark eyes is a problem solver built for a complicated world. Octopuses can open jars, escape tanks, and remember human faces. An octopus has no bones, 3 hearts, and arms that can taste what they touch. Yet its intelligence is what often leaves scientists most astonished. In aquariums, some have learned to unscrew lids, slip through tiny gaps, and move objects in ways that look almost planned. They can explore a container, test its edges, and find the weak point without being shown what to do. Their nervous system is also deeply unusual. Much of it is spread through the arms, so each limb can carry out complex actions, while the central brain coordinates the larger goal. Keepers have reported individuals that react differently to different people, as though they remember who brings food and who causes disturbance. This is not a creature shaped like us, or even closely related to us. It is a separate experiment in intelligence built in the ocean, soft-bodied and strange, proving that cleverness can evolve along a very different path. Dolphins call one another with signature whistles, almost like names. A young dolphin develops a personal sound early in life. That whistle becomes closely associated with its identity, and other dolphins can copy it when they need to get that individual's attention. This discovery changed how many people think about communication in the sea. These are not random squeaks drifting through the water. They are signals used inside social lives that can last for decades. Dolphins live in fluid groups, where companions split apart and meet again across large areas. A sound that points to one individual is useful in a world where vision is limited and distance matters. Scientists have played recorded whistles back to dolphins, and the animals often respond most strongly to those of familiar companions. It suggests recognition carried through sound, shaped by memory and relationship. Beneath the surface, where light fades quickly, a dolphin's world may be held together by voices that identify who is near. Elephants can recognize themselves in mirrors, a rare mental skill. Many animals react to a reflection as though another creature has appeared. Elephants can do something more unusual. In carefully designed tests with large mirrors, some individuals have investigated their own bodies in ways that suggest self-recognition. One famous elephant used the mirror to touch a mark placed on her head, a place she could not normally see. That matters because it hints at an awareness of the body as the self, rather than simply a moving shape. Elephants already show deep social knowledge in the wild. They remember companions, respond to distress, and seem to recognize the remains of their own kind. Mirror recognition does not prove they think like humans, but it adds another piece to a remarkable picture. Their minds appear tuned to identity, memory, and social connection. When an elephant studies its reflection, the moment feels simple, yet the thought behind it may be very deep indeed. Chimpanzees have learned to use tools in different cultural traditions. In one forest, a group may crack nuts with stones. In another, chimps may fish for termites with carefully prepared sticks. Elsewhere, they use leaves as sponges to soak up water. These behaviors are not spread evenly across all chimpanzees, which is what makes them so fascinating. They are learned socially, passed from one generation to the next inside particular communities. A young chimp watches older group members closely, then practices the same technique until it becomes skillful. That pattern looks very much like a culture, though it is not built from speech or writing. It is built from attention, imitation, and patience. The tools themselves are simple, but the tradition around them is rich. Scientists studying different groups have found local habits that can persist for years. Each community carries its own practical knowledge. In the forest, intelligence is not only inside one skull, it can live between minds. Bees can understand the idea of zero in simple tests. For a brain smaller than a sesame seed, this is a stunning achievement. Researchers trained bees to choose images with fewer objects in exchange for a sweet reward. Once they learned the rule, the insects were shown an empty image. Many chose it as less than one, which suggests they treated nothing as part of a numerical scale. Zero is difficult because it is not a thing you can point to. It is the absence of things, turned into an idea. Human children take time to grasp it, and many animals never show clear evidence of understanding it at all. Bees do not sit and calculate like tiny mathematicians, of course. Their minds are built for finding flowers, remembering routes, and making rapid choices in flight. Yet this experiment revealed that even a very small nervous system can represent quantity in a surprisingly abstract way. Ravens can plan for the future, even when food is not visible. A raven may choose a tool it does not need now because it will become useful later. In experiments, these birds have selected objects that can open a reward box after a delay, even when the box is absent at the time of choosing. That is remarkable because planning requires more than memory. It means holding a future situation in mind and preparing for it before the need arrives. Ravens also live complicated lives, hiding food, watching rivals, and forming long-term social bonds. In the wild, a bird that stores food must remember not only where it placed it, but who may have seen the hiding place. This creates a world full of strategy. Their intelligence is often compared with that of apes, although their brains are built very differently. A raven waiting on a branch may seem still, but its mind may be arranging possibilities that have not happened yet. Dogs can learn hundreds of human words through patient training. Some dogs have learned the names of toys at a scale that seems almost unbelievable. In famous studies, gifted individuals could fetch the correct object from a large collection after hearing its name only a few times. One border collie learned more than 1,000 labels and could sort some objects by category. This does not mean dogs understand language exactly as humans do. Their skill is more focused, tied to sound, attention, and reward. But it shows how deeply domestic dogs have adapted to human communication. They watch our posture, follow our gaze, and listen for meaningful patterns in our voices. A word can become a bridge between two species, carrying intention from a person to an animal mind. What makes this especially moving is the partnership behind it. The learning depends on trust, repetition, and shared attention. A dog waiting beside a pile of toys may be listening more carefully than we realize. Parrots can use words meaningfully, not just copy sounds. A parrot's voice can sound like mimicry, but some individuals have shown something far more intriguing. The African grey parrot Alex became famous because he could label colors, shapes, materials, and quantities during controlled work with researchers. When shown objects, he did not simply repeat phrases at random. He answered questions in ways that matched what he saw. He could also ask for things, reject items, and sometimes correct a trainer when the interaction did not go his way. This matters because parrots evolved vocal learning for social life in flocks, not for human conversation. Their brains are arranged differently from ours, yet they can connect sounds with concepts through careful teaching. The result feels like a small window into another kind of mind. A bird perched on a stand may not be speaking like a person, but it may be using sound with intention, attention, and surprising understanding. Honeybees teach each other flower locations through waggle dances. Inside a hive, a returning forager can perform a moving signal that tells others where to fly. The dance includes direction, distance, and the value of the food source. Its angle relates to the position of the sun. Its duration helps indicate how far the flowers are. Other bees follow closely, reading the movements with their antennae in the darkness of the hive. This is one of the most famous discoveries in animal communication because the message points to something outside the body, beyond the immediate space. A bee is not merely excited by nectar. It is giving navigational information that others can use. The colony depends on this exchange because flowers shift with weather and season. A good discovery must be shared quickly. In that warm, crowded hive, a tiny dancer turns personal experience into public knowledge. The result is a living system that searches the landscape through thousands of working minds. Animal intelligence has evolved in many remarkable directions. For a long time, people imagined intelligence as a single scale with humans at the top. That view is too simple for the living world. A squirrel that remembers hidden food, a spider that solves a hunting route, and a whale that learns a song are not competing in the same exam. Each mind is shaped by the problems its body and environment demand. Flight creates one kind of intelligence. Social life creates another. Hunting, migration, parenting, and survival all carve different mental tools. This is why comparing animals by human standards can hide what makes them extraordinary. A creature may fail at a task made for hands, yet excel at sensing patterns no person could notice. Intelligence is not always about language or machines. Sometimes it is memory. Sometimes it is timing. Sometimes it is cooperation. Nature has not built one road toward thought. It has built many. New Caledonian crows make hooked tools from twigs and leaves. On islands in the South Pacific, these birds have become master tool makers. They do not merely pick up sticks and poke at food. They shape materials with care. A crow may cut a strip from a plant, trim it, and form a tiny hook that can pull grubs from holes in wood. Some tools are made from twigs with natural curves, while others are crafted from the barbed edges of leaves. Young birds appear to learn by watching and practicing, which means the skill has a social life as well as an individual one. What makes the hook so impressive is its purpose. A straight stick can probe, but a hook can grip. That small change turns a simple object into a specialized instrument. Human beings once saw tool-making as a mark of our own uniqueness. These crows show that invention can also come on black wings in a forest far from any workshop. Some fish can recognize individual human faces in experiments. Fish are often treated as simple creatures, but some studies have challenged that assumption in a striking way. Archerfish were trained to choose a particular human face shown on the screen. They selected by spitting a jet of water at the image. When the target face was mixed with many unfamiliar faces, the fish still picked the right one with surprising accuracy. This is astonishing because these animals do not have the same brain structures humans use for face recognition. They also did not evolve around human faces, so the task was artificial and unfamiliar. Yet they managed it by using visual patterns well enough to separate one person from another. In the wild, archerfish need sharp vision to shoot insects from overhanging plants. That ability may help explain their performance. A fish watching through the water may be doing more than reacting. It may be noticing details that we never expected it to process. Rats laugh in ultrasonic chirps when they are gently tickled. The sound is too high for human ears to hear without special equipment, but it is there. Young rats produce rapid, high-pitched calls during playful handling and social play. When researchers tickle them in a careful way, many will return for more, as if seeking the experience again. These chirps are linked to positive emotion and playful arousal, not fear. The discovery matters because it opens a door into the emotional lives of animals that are often overlooked. Rats are social, curious, and capable of learning from one another. Their play is not random movement. It helps young animals practice social rules and build flexible responses. The idea of a laughing rat may sound amusing, but it also carries a deeper lesson. Joy is not a luxury found only in large or familiar animals. It can exist in a small body, racing through bedding, making happiness in a frequency we cannot hear. Pigeons can distinguish painted art styles after careful training. In experiments, pigeons have learned to tell paintings by different artists apart. After training with examples, they could sort unfamiliar images into the correct artistic category more often than chance. This does not mean a pigeon stands before a canvas and feels moved by brushwork, but it does show that the bird can detect complex visual patterns across many images. Pigeons are highly visual animals. They navigate long distances, recognize landmarks, and process fine details quickly. Their brains are not like ours, yet they can classify images in ways that seem surprisingly sophisticated. The art experiment is memorable because it uses a human cultural object to reveal an animal skill. A pigeon pecking at a screen may look simple, but it is comparing shapes, colors, and arrangements with enough consistency to make a judgment. Once seen as ordinary city birds, pigeons turn out to carry a visual intelligence hidden in plain sight. Orcas pass hunting techniques through families across generations. Different groups of orcas can live in the same ocean, yet behave almost like separate cultures. Some specialize in fish. Others hunt marine mammals. Some use waves to wash prey from ice, while others strand themselves briefly on beaches in carefully timed attacks. These methods are not simply instincts triggered by hunger. Young orcas learn by staying close to relatives and watching the adults perform difficult techniques again and again. A calf may spend years absorbing the rules of its family's way of life. The knowledge is carried by mothers and close kin, which makes social learning essential to survival. This is why losing older individuals can be so damaging. They may hold decades of practical experience. An orcapod is not just a group of predators moving through water. It is a community with inherited skills, shared calls, and learned habits. Their intelligence is written not only in the brain, but in the family line. Sperm whales use clan dialects that identify their social groups. In the deep ocean, these giants communicate with patterns of clicks known as codas. Different social clans use different rhythmic patterns, almost like acoustic badges. A whale can hear a sequence and gain information about group identity, even across dark water, where vision is nearly useless. These clans may include thousands of individuals spread over huge areas, yet their shared sound patterns help hold them together. The clicks are produced with powerful biological machinery inside the head, and they can travel great distances underwater. What makes this especially fascinating is the cultural aspect. Calves learn the patterns from the whales around them. Over time, a dialect becomes part of belonging. Sperm whales already live lives that are difficult for humans to imagine, diving into darkness and returning with knowledge we cannot see. Their social world is carried in sound. To listen closely is to hear identity moving through the sea. Gorillas can learn signs and express simple emotional ideas. The most famous signing gorillas sparked both admiration and debate. Researchers reported that some individuals learned hand signs for objects, actions, and feelings through long relationships with human caretakers. The science around these claims is carefully discussed because ape language studies are difficult to interpret. Yet the broader lesson remains powerful. Gorillas can understand routines, form strong bonds, and communicate preferences with intention. Even without formal signs, they use posture, facial expression, touch, and vocal sounds in rich social ways. Their emotional lives are visible in family groups, where infants cling to mothers, youngsters play, and adults respond to tension. A sign used by a gorilla does not make it human language, but it can reveal a mind trying to connect across a species boundary. That possibility is moving because gorillas are usually imagined through strength. Look longer, and what stands out is not power, but sensitivity, shaped by a deeply social life. Capuchin monkeys crack nuts with stones chosen for the job. In parts of South America, these small monkeys place hard palm nuts on stone anvils and strike them with heavy rocks. The work is demanding. A capuchin must select a suitable hammer, carry it, position the nut, and hit with enough force to open the shell without losing the food. Some stones are better than others, and experienced monkeys appear to choose tools that match the task. Youngsters watch adults and practice clumsily before they become skilled. The scene feels almost ancient, like a glimpse of problem-solving at its practical roots. There is no factory, no spoken instruction, and no written plan. There is only hunger, material, memory, and repeated effort. Archaeologists have even studied old capuchin nut-cracking sites because the stones can leave traces over time. A monkey lifting a rock may seem like a small moment, but it shows intelligence meeting the physical world with patience and force. Sea otters use rocks as tools while floating on their backs. A sea otter feeding up a surface can look almost relaxed, yet it may be doing something highly skilled. It often balances a shellfish on its chest and strikes it with a stone held between its paws. Some otters keep a favored rock tucked under loose skin beneath the forearm, ready for later use. That detail turns a simple action into something more personal. The animal is not only using a tool, it may be carrying equipment through its day. Hard-shelled prey can be difficult to open, and the otter's solution is beautifully direct. It brings the problem to the surface, steadies itself in rolling water, then hammers until the meal is accessible. Mothers teach pups by example, and young otters improve through long practice. In a cold ocean where every calorie matters, tool use becomes survival. The sight is charming, but beneath the charm is a clever mammal solving physics with stone, balance, and persistence. Some ants farm fungi in underground gardens with remarkable care. Deep below the forest floor, leafcutter ants maintain living farms that depend on constant attention. Workers cut pieces of fresh leaves and carry them home, not to eat directly, but to feed a cultivated fungus. The colony relies on this crop as its main food source, and different ants perform different tasks to keep the system alive. Some clean the garden. Some remove waste. Some defend the nest against invading microbes. The relationship is ancient, and over time the ants and their fungus have become closely linked. The leaves are prepared like compost, then placed where the fungus can grow. If harmful mold appears, workers act quickly to control it. This is agriculture without human hands, barns, or plows. It is careful, organized, and astonishingly precise. A trail of ants carrying green fragments may look like simple industry. In reality, it is the visible edge of a hidden civilization built around farming. Termites build towers that manage airflow without central planning. A termite mound can rise from the ground like a small earthen fortress, but its greatest wonder is hidden inside. The colony needs stable conditions for its residents and for the fungus some species cultivate. Yet no single termite carries the blueprint. Instead, thousands of tiny builders respond to local cues such as air movement, humidity, and chemical traces. Each small action changes the mound, and those changes guide the next actions. The result can be a structure that breathes. Warm air rises through channels, cooler air moves through lower passages, and the nest's internal climate becomes easier to control. Engineers have studied these mounds because they reveal how complex design can emerge without a central architect. A termite does not understand the whole tower. It simply follows rules shaped by evolution. Together, the colony creates architecture that solves problems far beyond the awareness of any individual insect. Wolves cooperate by reading each other's movements during hunts. A wolf pack does not hunt as a crowd of identical animals rushing forward. Each member watches the others, adjusts position, and responds to subtle changes in the chase. Some may pressure prey from behind, while others angle toward escape routes. The success depends on timing, stamina, and social awareness. A single wolf can be powerful, but group hunting allows the pack to take on animals that would be dangerous alone. This cooperation is rooted in family life. Pack members know one another, learn each other's habits, and share the outcome when a hunt succeeds. Their communication is not only in howls. It is in glances, body posture, speed, and spacing. A pause or turn can shift the whole pattern. In the snow or open country, the hunt becomes a moving calculation. What looks like wild pursuit is also teamwork shaped by experience, hunger, and trust. African grey parrots can understand color, shape, and number. The most famous example was Alex, a bird whose work with researchers changed public ideas about avian intelligence. When shown objects, he could identify properties such as color and shape, and he could answer questions about small quantities. His responses were not perfect, and they required years of patient training, but they were far beyond simple mimicry. He could tell the difference between items that were alike and items that were different. He sometimes asked for objects he wanted, and he appeared frustrated when sessions became repetitive. This mattered because it suggested that a bird brain could connect spoken sounds with concepts in a flexible way. African greys are naturally social and vocal, which gives them a strong foundation for learning sound patterns. Still, the leap from repeating a word to using it appropriately is enormous. In that leap, scientists glimpsed a mind that could compare, choose, and understand. Chimpanzees make leaf sponges to drink from hidden water. In dense forests, water can collect in tree holes where lips cannot easily reach. Some chimpanzees solve this by folding leaves into a soft wad, dipping it into the hollow, and sucking out the absorbed liquid. The tool is simple, but the behavior is rich with meaning. The chup must select material, shape it, use it, and understand that it can carry water from a place the mouth cannot access. Youngsters learn by watching older members of the group. Over time, the technique becomes part of local knowledge, useful in a habitat where dry periods can make water harder to find. A leaf that might look like forest litter becomes a sponge because a mind has given it a job. This kind of tool use reveals intelligence in ordinary moments. It is not dramatic like a hunt. It is practical, quiet, and deeply revealing. Survival often depends on such small acts of invention. Bonobos share food to build social bonds after conflict. Among bonobos, food can become more than nutrition. It can be a social tool. These apes are famous for using contact, play, and sharing to reduce tension within the group. After disagreement, a gesture of tolerance around food may help restore calm. This matters because their societies are highly social, and cooperation depends on managing relationships. Bonobos are close relatives of chimpanzees, yet their social style is often different. They tend to rely more on bonding and reconciliation, especially within female networks. A piece of fruit offered or accepted can signal that danger has passed. The moment may seem small, but in a close-knit community, small signals carry weight. Scientists study bonobos because they reveal that intelligence is not only about tools or puzzles. It is also about emotional navigation. Knowing when to share, when to approach, and when to repair a relationship can be as important as any physical skill. Horses can read human facial expressions and remember them. A horse meeting a person is not simply seeing a shape. It can pay attention to the emotional information carried in a face. In studies, horses shown images of angry human expressions later reacted differently when they met that person, even after a delay. Their heart rates and gaze patterns suggested that the earlier expression mattered. This is impressive because horses and humans do not share the same facial anatomy or social signals in every detail. Yet domestication placed them beside us for thousands of years, creating a strong reason to understand our moods. A nervous rider, a calm handler, or a threatening stranger can all affect what happens next. Horses are prey animals, so sensitivity to expression and body language has deep survival value. Their intelligence often shows through attention rather than dramatic action. A horse standing still with its ears forward may be reading the room with more care than we imagine. Goats can ask humans for help using gaze and posture. When a goat faces a problem it cannot solve alone, it may turn toward a person and look back at the task, as if drawing attention to it. This kind of behavior has been studied with containers that the animal learned to open. When the container was made impossible to open, goats often shifted their gaze between the human and the reward. That is remarkable because it suggests they understand people as potential partners in solving a problem. Goats were domesticated long ago, and their lives around humans may have sharpened this ability. They are often curious, persistent, and quick to learn how objects work. A goat asking for help does not need words. Its body becomes the message. It looks, waits, and points with attention. The moment may seem playful, but it reveals a flexible social intelligence. The animal understands that another mind in the room may change the outcome. Sheep can recognize familiar faces after long periods apart. A sheep's face may look expressionless to many people, But sheep are expert face readers in their own social world. They can remember other sheep and human handlers, and they can distinguish familiar individuals from unfamiliar ones. In experiments, they have learned to recognize faces from photographs, which is surprising for an animal often unfairly treated as simple-minded. This ability makes sense when you consider flock life. Knowing who belongs, who is safe, and who has been encountered before can matter greatly. Sheep form social preferences, and separation from familiar companions can be stressful. Their visual system is tuned for wide awareness, with eyes placed on the sides of the head, yet they still manage detailed recognition. Memory gives stability to the flock. A sheep in a field is not surrounded by interchangeable bodies. It lives among known companions, and its mind carries a gallery of faces that can remain meaningful over time. Cuttlefish can remember what they ate, where, and when. A cuttlefish lives a short life, yet its memory can be surprisingly rich. In experiments, individuals learned that certain foods appeared in certain places after different waiting times. They adjusted their choices depending on what had been available and how much time had passed. This resembles a form of episodic-like memory, the ability to connect what happened with where and when it happened. That is striking in an animal so distant from mammals. Cuttlefish are active hunters with soft bodies and complex skin displays. They must track opportunities in changing environments, and memory helps them avoid wasting effort. If a favorite prey item takes longer to return, waiting may be smarter than checking too soon. Their intelligence is not built for a long future. It is built for precision in the present. Each remembered meal becomes part of a map of possibility, held inside a creature that can vanish against the seafloor in seconds. Octopuses may dream with shifting colors across their skin. When some octopuses rest, their skin can ripple through patterns that resemble those used while awake. Dark flashes, pale patches, and sudden textures appear across the body. Scientists do not yet know exactly what this means, but the possibility is captivating. Octopus skin is controlled by the nervous system through tiny pigment organs and muscles. During active life, those changes help with camouflage, signaling, and hunting. When they appear during sleep-like states, they raise a fascinating question. Is the animal replaying experiences? Is its nervous system practicing patterns? Or are the colors simply byproducts of sleeping brain activity? The answer remains uncertain, but the sight is unforgettable. A sleeping octopus may briefly display the visual language of its waking world. Because its body shows internal changes so openly, it gives observers a rare glimpse into the borderland between rest and experience. The ocean's most alien intelligence may even dream in color. Spiders can plan detours while stalking hidden prey. Some jumping spiders are tiny hunters with extraordinary visual attention. When prey is visible but blocked by a difficult path, certain species can leave the direct line of sight and take a route that leads around the obstacle. That requires more than lunging at movement. The spider must remember where the prey was, abandon the obvious path, and follow a sequence that may temporarily hide the target. For an animal with such a small nervous system, this is astonishing. Its world is built from vibration, distance, and sudden motion, yet it can still solve a spatial problem. These spiders often pause before moving, as if assessing the scene. Their large, forward-facing eyes gather detailed information. Then the body acts with precision. The detour may last only moments, but it reveals a mind capable of holding an unseen goal. Even a creature small enough to rest on a fingertip can hunt with strategy. Jumping spiders make decisions with brains smaller than sesame seeds. The scale is almost impossible to appreciate. A jumping spider's brain is tiny, yet it supports sharp vision, careful stalking, and rapid decisions. These animals can judge distance before leaping, identify prey, and sometimes choose between possible routes. Some species even specialize in hunting other spiders, which demands caution because the prey can be dangerous. Their eyes provide a wide field of awareness, while the central pair gives unusually detailed focus. When a spider turns to look, it is gathering information with remarkable care. Its leap is not a random spring. It is aimed, timed, and adjusted to the target. The smallness of the brain makes the performance more impressive, not less. It shows that intelligence does not always require size. Sometimes evolution builds efficient systems that do exactly what survival demands. In a miniature hunter, thought becomes compact, fast, and beautifully tuned to action. Border collies can learn object names with astonishing speed. Some border collies have shown a rare talent called fast mapping. After hearing a new word only a few times, they can connect it to a new toy among familiar ones. This skill is not common in all dogs, but in gifted individuals it can be breathtaking. The breed was shaped for herding, where attention to human signals and rapid response are essential. That background may help explain why some of these dogs become such strong word learners. A trainer can place a new object with others, say its name, and the dog may infer that the unfamiliar word belongs to the unfamiliar item. That is a clever form of reasoning. It uses exclusion rather than simple repetition. The dog is not merely obeying a sound. It is sorting possibilities. In a living room full of toys, a border collie may perform a mental act that feels strikingly close to early language learning. Dolphins understand pointing, gestures, and artificial symbol languages. In research settings, dolphins have learned to follow human hand signals and respond to sequences of symbols. They can distinguish differences in word order when trained with artificial languages, which means the arrangement of signals can matter to them. A command for taking one object to another is not the same as reversing the action. That level of comprehension suggests a powerful ability to process relationships. Dolphins are naturally social animals, and their lives in water depend heavily on sound, movement, and coordinated action. Training studies build on those capacities by creating shared signals between species. The result is not human speech, but it is communication with structure. A dolphin waiting at the surface, listening and watching, can translate a human signal into an action it has learned to perform. The deeper wonder is not that it follows instructions. It is that two very different minds can meet through a carefully built language. Humpback whales share new feeding tricks across entire oceans. A feeding method can begin in one region and later appear in many others, spreading through observation and social contact. One famous example involves whales striking the water with their tails before bubble feeding. The behavior expanded through populations over years, suggesting that individuals learned from one another rather than inventing it separately every time. Humpback whales already have complex seasonal lives, moving between feeding and breeding areas across immense distances. When a useful technique spreads through that wide network, it shows how culture can move through the sea. The learning is not written down or taught in a classroom. It travels through presence, attention, and repeated success. A whale sees another whale feed effectively, then adopts the method. Over time, the ocean becomes a place where knowledge can ripple outward. These animals are not simply following fixed instincts. They are watching each other, updating their behavior, and carrying discoveries across blue distances. Meerkats teach pups how to handle dangerous scorpions safely. In the desert, young meerkats must learn to eat prey that can fight back. Adults help by bringing pups scorpions in different conditions. Very young pups may receive dead prey. Older ones may receive scorpions with the stinger removed. More experienced pups are given live prey and must practice dealing with it. This gradual method looks remarkably like teaching because the adult changes its behavior according to the youngster's ability. The lesson is practical and urgent. A mistake with venomous prey could be costly. By adjusting the challenge, adults give pups a safer path toward skill. Meerkat groups live cooperatively, and helpers often care for young that are not their own offspring. In such a society, knowledge can be shared through action. A pup learning to handle a scorpion is not simply playing with food. It is being guided through a survival lesson, step by careful step, under the eyes of the group. Prairie dogs use alarm calls with surprisingly detailed information. When danger appears, these small rodents do more than shout that something is wrong. Their calls can carry information about the type of predator, and experiments suggest they may encode details about size, shape, or color. A human walking through a prairie dog town might trigger a different pattern than a hawk overhead or a dog nearby. This is remarkable because it suggests a communication system tuned to specific threats. The animals live in open landscapes where early warning is vital. A precise alarm helps neighbors choose the right response. Should they dive underground at once, watch the sky, or track a ground predator's movement? The answer depends on the caller's information. Prairie dogs spend much of their lives in social colonies, where attention to neighbors is part of survival. Their voices turn the landscape into a shared warning network. A small bark from a burrow mound can contain a surprising amount of meaning. Baboons can judge social rank by listening to calls. In a baboon group, status shapes access to food, mates, and safety. Individuals must understand who outranks whom, even when they are not directly involved. Experiments using recorded calls have shown that baboons react strongly when the sounds suggest an unusual social reversal, such as a lower-ranking animal appearing to dominate a higher-ranking one. That reaction implies that they carry a mental map of relationships inside the group. They are not merely remembering who is stronger than they are. They track relationships, among others. This ability is valuable because primate society can be tense and shifting. Knowing which alliances matter helps an animal avoid mistakes. A call heard from behind a bush may reveal more than noise. It may signal that the social order is behaving normally, or that something surprising has happened. For baboons, intelligence is deeply social. The mind must listen not only for danger, but for politics. Macaques wash food in water and pass the habit onward. On a Japanese island, researchers observed a young macaque washing sweet potatoes before eating them. The behavior then spread through the group, especially among younger animals and their close companions. Over time, it became one of the classic examples of a learned animal tradition. The act itself is simple. Sand makes food unpleasant, and water removes it. Yet the importance lies in how the habit moved from one individual to others. A new solution appeared, proved useful, and became part of group behavior. This shows that innovation can begin with a single, curious animal. It also reveals how social learning can shape daily life in a population. Not every member adopted the practice at once, which makes the spread feel even more natural. Culture does not have to mean art or language. Sometimes it begins with a young monkey discovering that a meal tastes better after a dip in the sea. Japanese tits combine calls to create simple warning messages. These small birds use different sounds for different meanings, and research suggests they can combine calls in meaningful order. One call may alert others to danger. Another may encourage them to approach. When played together in the normal sequence, the birds respond appropriately, scanning for a threat and moving closer. When the order is reversed, their response weakens. This is fascinating because it hints at a basic form of compositional communication, where separate signals combine to create a larger message. Human language uses this principle constantly, but finding anything similar in wild animals is rare and important. For a small bird in woodland, clear communication can save lives. A snake near the nest requires a different response from a passing disturbance. The bird's calls help coordinate the group. A few notes in the trees may sound delicate to us, but to another bird they can carry instructions with real urgency. Scrub jays hide food differently when another bird is watching. A scrub jay storing food behaves like a creature that understands the risks of being observed. If another bird watches it hide a meal, the storer may later return and move the food to a new location. This behavior is especially strong in birds that have stolen from others before, which makes the finding even more intriguing. Experience as a thief may help a jay anticipate theft by another. That suggests a sophisticated link between memory, perspective, and future protection. Caching food is essential because stored meals can support survival during lean times. But a hidden treasure is only useful if it stays hidden. A watching rival turns memory into a security problem. The jay must track not just the hiding place, but the social situation around the hiding. In that small act of moving food after being watched, we glimpse a mind shaped by secrecy, suspicion, and careful planning. Clark's nutcrackers remember thousands of seed hiding places. In mountain landscapes, these birds bury pine seeds across wide areas before winter. Months later, often beneath snow, they return and recover many of them. The memory involved is extraordinary. A single bird may create thousands of caches, and its survival depends on finding enough of them when food is scarce. It uses landmarks in the environment, building a detailed spatial map across rugged terrain. This is not the kind of memory that recalls a psalm or face. It is a living map of stored energy spread through the world. The bird must update that map while weather changes, snow falls, and seasons pass. Some forgotten seeds sprout into trees, which means the bird also helped shape the forest around it. A nutcracker flying over a slope may be carrying an invisible atlas inside its head. Each dip and ridge can point toward a meal hidden long ago. Pigeons can navigate home using smell, sun, and magnetism. A pigeon released far from its loft can still find its way back across unfamiliar country. Scientists have studied this ability for decades, and the answer appears to involve several systems working together. The sun can provide direction. Smells carried by winds may help build a map of place. Earth's magnetic field may offer another layer of guidance. The bird does not rely on one simple compass. It combines cues, and the balance may change depending on conditions. This makes homing both practical and mysterious. Pigeons have served as messengers because people learn to trust their return. Yet the bird's inner experience remains hard to imagine. It rises into the air, circles, gathers information, then chooses a route home. Streets, fields, and rivers pass below, but the real navigation is happening inside the animal. A common city pigeon belongs to a lineage of travelers with senses reaching beyond our own. Dogs notice when humans point, even as tiny puppies. A young puppy can often follow a human pointing gesture without months of formal training. This ability is special because pointing is not just movement. It directs attention towards something else. Many animals struggle with this kind of signal, especially when it comes from another species. Dogs, however, have lived beside humans for so long that their social attention has been shaped around us. Even very young pups can look where a person indicates and search there for a reward. This helps explain why the bond between dogs and people feels so natural. A hand gesture, a glance, or a tone of voice can become meaningful. The puppy is not reading a sentence. It is reading intention through the body. That skill made dogs useful partners in work and beloved companions at home. From the beginning of life, many seem ready to enter a shared world of attention with human beings. Cats can recognize their names, even when they seem indifferent. A cat may sit still when called, which can make people wonder whether it understands at all. Experiments suggest that many cats do recognize the sound of their own names. Researchers played a series of similar words, then the cat's name, and measured subtle responses such as ear movement, head turns, or tail shifts. The animals often reacted more to the familiar name than to the surrounding sounds. The important point is that recognition is not the same as obedience. Cats were domesticated under different pressures than dogs, and their relationship with humans has often allowed more independence. A cat may know exactly what sound refers to it, yet choose not to come. That choice is part of its charm and part of its nature. Intelligence is easy to miss when we expect performance on command. Sometimes the mind is there, listening from the windowsill, deciding whether the request is worth answering. Pigs can use mirrors to find hidden food. In a clever experiment, pigs were allowed to explore a mirror and learn how reflections worked. Later, food was hidden where it could not be seen directly, but its reflection was visible. Some pigs used the mirror information to turn away from the mirror and go to the real location of the food. This shows more than simple interest in a shiny surface. It suggests they could use reflected space to guide action. Pigs are naturally curious animals with strong memories and active problem-solving abilities. They root, explore, and investigate their surroundings through smell and touch, but vision can also become part of the puzzle. Using a mirror in this way requires understanding that the image relates to the world behind them. The food is not in the glass. It is elsewhere, and the reflection is a clue. That leap makes the pig's success both practical and deeply impressive. Cows form friendships and may become stressed when separated. A herd is not just a collection of animals grazing side by side. Cows can develop preferred companions, spending more time near certain individuals and showing calmer behavior when those partners are present. When separated from a familiar friend, some show signs of stress through changes in heart rate, movement, or vocalization. This matters because it reveals emotional structure inside an animal many people view mainly through farming. Social bonds help create stability. A trusted companion can make unfamiliar situations less frightening. In a herd, knowing who is comfortable to stand beside can shape the animal's daily experience. Cows also recognize individuals and remember past interactions, which supports these longer relationships. Their intelligence is not dramatic in the way of tool use, but it is deeply social. A cow resting beside a chosen companion is showing that attachment is not limited to animals we usually call clever. Feeling safe together is also a kind of wisdom. Ducks can grasp same and different shortly after hatching. A duckling enters the world ready to learn at remarkable speed. Soon after hatching, it can imprint on a moving object and follow it as though it were a parent. Researchers used this powerful learning window to test something deeper than simple following. They showed ducklings pairs of shapes or colors, then later gave them new pairs they had never seen before. Some pairs matched, others did not. The ducklings tended to follow the relationship they had first learned, not the exact objects. If they had learned sameness, they chose a new matching pair. If they had learned difference, they chose a new mismatched pair. That is astonishing, because it suggests a very young bird can notice an abstract relationship. It is not just memorizing a picture, it is learning a rule. Before it has much experience of the world, a duckling's brain is already sorting patterns with surprising sophistication. Bumblebees can learn by watching other bees solve tasks. A bumblebee may look like a simple forager, but experiments have revealed a mind that can learn from observation. In one study, bees watched trained companions move a tiny ball to a target in exchange for a reward. Later, the watching bees often solved the task themselves. Even more impressive, some improved on what they had seen by using a closer ball instead of copying the exact movement. That suggests they were not blindly imitating. They understood enough of the goal to find a better route. This matters because social learning was once thought to require larger brains and more complex societies. Bumblebees show that even a small nervous system can absorb useful information from another individual. In the wild, such learning could help them find flowers, handle difficult blossoms, or adjust to changing conditions. A bee watching another bee is not wasting time. It may be gathering knowledge. Wasps can recognize individual faces within their own colonies. Paper wasps live in societies where knowing who is who can reduce conflict and support cooperation. Their faces carry distinctive markings, and some species can learn those patterns with impressive precision. In experiments, wasps were trained to recognize individual face images better than other visual patterns. This skill makes sense in colonies where dominance relationships matter. If a wasp remembers a neighbor's identity, it does not have to fight the same contest again and again. Recognition saves energy and helps the group function. What makes this especially surprising is that wasps have tiny brains, yet they can perform a task that sounds almost human. They are not simply reacting to motion or scent. They are using visual details to identify individuals. A paper nest may look chaotic from the outside, but inside it, there is social memory. Each marked face can carry a history, and each remembered encounter can shape what happens next. Fruit flies weigh risk and reward before choosing food. A fruit fly can seem like a tiny impulse with wings, but its choices are more careful than they appear. When food is available in a risky place, the fly must balance hunger against danger. Laboratory studies show that flies change their behavior depending on internal state, past experience, and the level of threat. A hungry fly may accept a risk that a well-fed fly avoids. If it has learned that a particular smell predicts punishment, it can steer away from it later. These decisions emerge from a brain with far fewer neurons than a human brain, yet the logic is recognizable. Need changes the value of reward. Experience changes the meaning of a cue. Danger changes the final action. That is decision-making in miniature. The next time a fruit fly circles a piece of fruit, it may not be acting randomly. It may be running a tiny calculation about survival. Cockatoos can unlock complex puzzle boxes through trial and memory. Some cockatoos have become famous for their mechanical curiosity. In experiments, they have faced boxes secured with several different locks, including pins, wheels, latches, and sliding bars. To reach a reward, a bird must discover how each part works, then complete the actions in the right sequence. The first success can take time, but once the solution is learned, the bird often becomes much faster. That reveals memory as well as exploration. It remembers which movement worked, which part shifted, and how the next step follows. If the order is changed, some individuals adjust instead of giving up. Cockatoos are naturally playful and persistent, which gives them a strong foundation for this kind of problem-solving. Their beaks and feet become tools for investigation. A locked box that might frustrate many animals becomes a challenge to be studied. The reward is food, but the deeper spectacle is curiosity made visible. Key parrots investigate objects with a curiosity rare in birds. In the mountains of New Zealand, key live in a world that rewards bold exploration. Snow, rock, changing weather, and scattered food create problems that are rarely solved by habit alone. These parrots are famous for tugging, prying, rolling, and testing almost anything they encounter. Their curiosity can be inconvenient for people, especially when they investigate backpacks or vehicles, but it reveals a powerful intelligence. A key often examines an object from several angles before deciding what to do. It may pull at a loose part, listen to the result, then try again differently. This style of investigation is valuable in a harsh environment where food can be hidden or unpredictable. Scientists have tested key on puzzles requiring cooperation, restraint, and flexible thinking, and the birds often surprise them. They remind us that intelligence can be playful without being aimless. Sometimes a mind learns by poking the world until it answers. Ravens remember fair and unfair partners during food trades. A raven can keep track of how another individual behaves in a deal. In experimental exchanges, these birds have been offered trades with human partners or other ravens. A fair partner gives the expected reward. An unfair one keeps the food or offers something worse. Later, ravens often prefer to interact with the partner that treated them well. This is striking because it shows memory tied to social judgment. The bird is not only remembering a face or event, it is remembering a pattern of trust. In the wild, ravens deal with competition constantly, especially around food. Knowing who can be tolerated and who should be avoided may save time and danger. Their social lives include alliances, rivalries, and careful observation. A raven watching another individual may be taking notes in its own way. Fairness may sound like a human concept, but the roots of reputation can appear in feathered minds too. Crows can recognize dangerous human faces for years. Researchers once captured wild crows while wearing a particular mask. Long after the event, crows reacted strongly when that same mask appeared again. They scolded, mobbed, and recruited other birds to join the warning. Even crows that had not been captured seemed to learn the danger from others. This shows a powerful combination of memory and social transmission. The bird remembers a specific human face, connects it with threat, and passes that information through the group. In busy human environments, that skill is extremely useful. Cities are full of people, vehicles, pets, and changing hazards. A crow that can identify a dangerous person without confusing everyone else gains a real advantage. The most remarkable part is the duration. Years can pass, yet the warning remains. A person may forget a brief encounter with a crow, but the crow may not forget the person. In its world, a face can become part of local history. Rooks can use stones to raise water levels. A rook faced with food floating out of reach can solve the problem by changing the environment. In classic tests inspired by an old fable, birds dropped stones into a tube of water until a floating reward rose high enough to grab. The clever part is not the stone dropping alone. It is the relationship between the stones, the water level, and the unreachable food. Some birds chose objects that sank rather than floated, which made the task work better. They also adjusted effort depending on how much the level needed to rise. This suggests a practical understanding of cause and effect. Rooks do not use tools much in the wild compared with some other corvids, which makes the laboratory success even more interesting. The ability was there, waiting for the right situation. A small stone became a way to move water, and water became a way to bring food within reach. Magpies have shown mirror recognition in carefully designed studies. A magpie is a bird with a busy social life and a sharp eye for detail. In a famous experiment, researchers placed a colored mark on a bird's body, where it could only be seen in a mirror. Some magpies used the mirror to notice the mark and then tried to remove it. That behavior has been interpreted as evidence of self-recognition. The finding attracted attention because mirror recognition had mostly been associated with a small set of mammals and a few other highly social animals. A bird passing such a test suggests that complex self-related processing can evolve in very different brains. There is still debate around what the test proves, but the behavior remains remarkable. The magpie did not simply attack the reflection or court it. It used the image to guide action toward its own body. A mirror turned into a question, and the bird seemed to understand where the answer was. Jays may imagine what rivals know before hiding food. A jay storing food has to think like a thief, especially if another bird is nearby. In experiments, scrub jays that had experience stealing from others were more likely to move their own caches after being watched. This detail is fascinating because it suggests that personal experience shapes suspicion. A bird that knows theft from the inside may be better at predicting it from another. Some researchers see this as a possible sign of perspective taking, though the exact mental process remains debated. What is clear is that the bird's caching behavior changes according to the social situation. It matters who was watching, what they could see, and whether the food remains vulnerable. The jay's world is full of hidden meals and hidden intentions. A seed pushed into the ground is not the end of the story. It begins a mental contest between memory, observation, and the possibility that another mind knows too much. Chimpanzees sharpen sticks for hunting small mammals in trees. In some communities, chimpanzees have been observed modifying branches into pointed tools and using them to jab into tree cavities where small nocturnal animals hide. This behavior is especially striking because it shows tool use in a hunting context. The chimp selects a branch, removes leaves or side twigs, and sometimes frays or sharpens the end with its teeth. Then it probes into a hollow, hoping to injure or extract prey. The method is not universal among chimpanzees, which suggests local learning rather than a simple species-wide instinct. It also reveals how flexible their feeding strategies can be. Hunting is often imagined as a chase, but here it becomes a careful act of preparation. The stick from the forest becomes an extension of the arm. The hidden space inside a tree becomes reachable. In that moment, a chimpanzee changes the terms of the hunt by reshaping the object in its hand. Orangutans can plan routes through forests before traveling. A male orangutan may announce his intended direction with long calls before he begins moving. Other orangutans can use those calls to adjust their own travel, which suggests the caller's path is not random. In the forest canopy, efficient movement matters. Food trees are spread unevenly, distances are difficult, and wasted energy can be costly. Orangutans have large mental maps of their home ranges, and they remember where fruit is likely to be available. Planning a route through such a landscape requires memory, timing, and spatial awareness. Their intelligence is often patient rather than showy. They move through branches with slow deliberation, but their minds may be working far ahead of their hands. A direction chosen in the morning can reflect knowledge gathered over months or years. In a forest that changes with seasons, an orangutan survives by remembering not just where it is, but where it should go next. Gorillas use walking sticks to test the depth of water. A gorilla wading through a swampy clearing may pick up a branch and use it in a way that looks startlingly practical. By placing the stick ahead, the animal can test how deep the water is before stepping forward. This kind of behavior has been observed in the wild, and it expands the image many people have of gorillas. They are not only powerful plant eaters, they are careful problem solvers moving through difficult terrain. Water can hide holes, unstable mud, or sudden depth changes, and a large body must avoid dangerous footing. The stick becomes a sensory extension, allowing the gorilla to gather information beyond arm's reach. It is a tool used not for food, but for safety. that distinction matters. Intelligence is not always about getting a reward immediately. Sometimes it is about avoiding a mistake. A branch in the hand becomes a question asked of the ground. Monkeys can understand simple money exchanges in laboratory games. In some experiments, capuchin monkeys learned to trade tokens for food. A token had no natural value, but inside the test it could be exchanged for something desirable. The monkeys learned which humans offered better returns, and they adjusted their choices accordingly. This kind of work reveals how flexible their understanding of value can be. The token is not food, yet it stands for food in a social exchange. That is a powerful step. Some studies also found that monkeys reacted strongly when rewards seemed unequal, especially when a neighbor received a better treat for similar effort. The findings are carefully interpreted, but they show that primates are sensitive to exchange, expectation, and outcome. A small disc placed in a monkey's hand can become part of an economic game. The animal gives it away because experience has taught it that value can travel through a symbol. Cleaner wrasse fish may pass mirror tests using body marks. These small reef fish live by removing parasites from larger animals, which makes attention to bodies central to their survival. In mirror experiments, some cleaner wrasse behaved in ways that surprised researchers. After seeing a colored mark on their own bodies in a reflection, they tried to scrape that part against a surface. The mark had been placed where it could not be seen directly, which made the mirror important. This result sparked debate because the traditional mirror test was designed around mammals and birds, not fish with very different bodies and motivations. Still, the behavior is hard to dismiss. It suggests these fish may connect the reflected image with their own physical state. At the very least, the finding forces science to ask better questions. Maybe self-awareness does not always look like a primate inspecting its face. In a reef fish, it may appear as a sudden attempt to clean an unexpected mark. Lemurs remember which group members make reliable social partners. Lemur society can be surprisingly strategic. In groups where grooming, support, and tolerance matter, individuals benefit from remembering who has been helpful before. Studies suggest that some lemurs track social relationships and choose partners based on past interactions. That ability is important because cooperation is not equally valuable with everyone. A reliable partner may provide support during tension or access to calm contact. An unreliable one may not be worth the effort. Lemurs are primates, but they belong to an older branch of the primate family tree. Their social intelligence gives scientists a useful window into how relationship tracking may have evolved. In their world, memory is not only about food or location. It is about individuals. Who shares space peacefully? Who responds when approached? Who can be trusted nearby? A lemur moving through its group carries a social map, and that map can guide choices day after day. Bats build mental maps for flying through darkness. A bat in flight is not simply reacting from one wing beat to the next. Many species use echolocation, sending out calls and listening for returning echoes. But those echoes also feed a larger understanding of space. As a bat travels through caves, forests, or city edges, it learns the arrangement of obstacles, roosts, feeding areas, and routes. Some bats can return to important locations over long periods, which suggests a durable spatial memory. Echolocation gives rapid information about what is nearby, while memory helps organize the broader world. Together, they allow the animal to move through darkness with astonishing confidence. The sound pulses are too high for most people to hear, yet for the bat, they are a stream of structure. A wall becomes an echo. A branch becomes a warning. A gap becomes a path. In darkness that would stop us completely, the bat's mind builds a usable world. Vampire bats share food with neighbors that helped before. A vampire bat feeds on blood, and missing a meal can become dangerous quickly. Because of that, food sharing can be a matter of life and death. These bats sometimes regurgitate blood meals to roostmates that failed to feed. The giving is not random. Individuals are more likely to help bats that have helped them before or close social partners they know well. This has made vampire bats an important example in studies of reciprocal cooperation. The behavior sounds strange at first, but the social logic is elegant. A fed bat gives up a little to save another from starvation. Later, the favor may be returned. Over time, stable relationships can form around mutual aid. Grooming also helps maintain these bonds. In the darkness of a roost, survival depends not only on flight and feeding, but on trust built through repeated acts of support. Dolphins cooperate with fishermen in a rare wild partnership. In one coastal region of Brazil, wild dolphins and human fishers have formed an extraordinary working relationship. The dolphins drive fish toward the shore, and the fishers watch for signals that tell them when to cast their nets. When the nets fall at the right moment, both sides can benefit. The fishers catch more fish, and the dolphins may capture fish confused by the netting. This is not a trained show. It is a local tradition involving wild animals and people who understand their movements. The dolphins use body cues, such as sudden dives or positions, and the humans learn to respond. The partnership has lasted across generations, which makes it a rare example of cooperation between species in daily life. It shows that intelligence can create shared opportunity without a common language. In the moving water, two very different hunters coordinate through timing, attention, and experience. Some dolphins use sea sponges to protect their beaks. In Shark Bay, some bottlenose dolphins carry marine sponges on their rostrums while foraging along the sea floor. The sponge appears to act like protective gear, shielding the sensitive skin as the dolphin probes rough or sharp surfaces for hidden fish. This behavior is mostly seen in certain family lines, and young dolphins learn it from their mothers. That makes it one of the clearest examples of tool use passed socially in wild dolphins. The technique takes effort. A dolphin must find a suitable sponge, detach it, position it, and continue hunting while wearing it. The reward is access to prey in places that might otherwise be difficult or uncomfortable to search. What looks unusual at first becomes completely practical once the problem is understood. A sea sponge becomes equipment. A mother becomes a teacher. A feeding habit becomes a tradition, carried through a watery community by learning rather than instinct alone. Belugas can imitate human speech patterns with uncanny accuracy. Belugas are sometimes called sea canaries because of their varied calls, clicks, and whistles. One captive beluga became famous when people heard sound that resembled muffled human speech. Researchers later studied the vocal behavior and found that the whale had altered its usual sound production in a way that approximated human-like rhythms. It was not speaking with meaning, but the imitation itself was remarkable. Producing such sounds required unusual control over the vocal tract and air pressure. Belugas are highly social animals that use sound constantly in their natural lives, so vocal flexibility is part of their biology. Still, copying the patterns of another species shows a special kind of learning. It reveals attention to sound shape, not just sound presence. A beluga in a pool, listening to human voices, managed to bend its own anatomy toward an alien pattern. The result was eerie, charming, and scientifically important. Seals can learn rhythms better than many animals tested. Rhythm may feel natural to humans, but keeping a beat is rare across the animal kingdom. Some seals have shown impressive sensitivity to rhythmic patterns, including the ability to learn and reproduce sequences of sounds. In studies with trained individuals, they could detect timing differences and adjust vocal output in ways that suggest strong auditory learning. This is interesting because seals are vocal mammals, especially during breeding seasons, where sound can carry social meaning. Their brains are tuned to hearing patterns in noisy environments, and that may support rhythmic ability. The finding also helps scientists ask why some animals can learn beats while others cannot. Is rhythm linked to vocal learning? Is it shaped by social communication? Seals give researchers a living clue. A seal bobbing in water may seem playful, but when it follows a pattern in time, it reveals a hidden bridge between animal sound and the roots of music. Sea lions can understand logical relationships between symbols. A trained sea lion named Rio became famous in cognitive research because she learned relationships among symbols and then made new connections without direct training. If she learned that one symbol matched a second and a second matched a third, she could later infer that the first and third belonged together. This kind of reasoning is called equivalence, and it is important because it shows flexible mental organization. The symbols themselves did not resemble natural objects in her environment. Their meaning came from the learned relationships between them. That makes the achievement more abstract than choosing a visible food reward. Sea lions are agile, social predators with strong learning abilities, but this task revealed something especially striking. A symbol could stand inside a web of meaning. Rio's success suggested that non-human animals may form categories and connections in ways once thought to be far more limited. Logic, in simple form, can swim. Manta rays have large brains and show curious social behavior. A manta ray moves through the water with wings wide as a small room, yet its mind may be just as remarkable as its body. Among fish, manta rays have unusually large brains relative to body size. They have been seen engaging in social interactions, visiting cleaning stations, and showing curiosity toward divers. Some individuals appear to return to particular places and interact in ways that suggest recognition and memory. Their behavior is difficult to study because they range across broad ocean spaces, but every discovery adds weight to the idea that these animals are not simple drifting giants. They investigate their surroundings, adjust behavior around others, and may have social preferences. At cleaning stations, they hover, while smaller fish remove parasites, which requires tolerance and repeated learning of safe places. A manta gliding overhead can feel almost silent and unknowable. Science is beginning to show that there is a complex mind moving with it. Sharks can learn routes and remember feeding locations. A shark's reputation often focuses on instinct, but research shows that many sharks learn from experience. They can remember areas where feeding opportunities occur and return to them over time. Some species follow regular routes through reefs or coastal regions, using sensory cues that may include smell, water movement, magnetic information, and local landmarks. Learning matters because prey is not evenly spread, and energy spent searching must be used wisely. In experiments, sharks can learn associations between signals and rewards, then retain that information. This does not make them mindless machines. It makes them adaptable predators. A shark moving through water is sampling a world rich with chemical trails and pressure changes. Its brain is built for that environment. Memory helps connect those cues with places and outcomes. The result is a hunter that does not simply wander until something appears. It can build knowledge of its range and use it again. Archerfish shoot water jets after calculating moving targets. An archerfish hunts with a weapon made from its mouth. It spots insects resting above the water, aims through the distorted boundary between water and air, and fires a jet that knocks prey down. The physics are difficult. Light bends at the surface, so the fish must correct for refraction. If the target is moving, the challenge grows. Some studies show that archerfish can adjust their shots and learn from experience. They can also recognize which target is worth shooting when multiple choices are present. The jet itself is shaped by precise mouth and gill movements, turning water into a focused projectile. This is not a lucky splash. It is a calculated strike from below. In a mangrove or stream, an archerfish sees a meal in another world and reaches it without leaving the water. Its intelligence appears in the moment when vision, timing, and pressure combine into one perfect shot. Goldfish can learn mazes and remember patterns for months. The idea that goldfish have almost no memory is one of the most persistent myths about animals. In reality, they can learn routes, distinguish colors and shapes, and remember trained tasks long after the first lesson. Maze experiments show that goldfish can find paths toward rewards and improve with practice. They can also respond to signals that predict feeding time. This makes sense when we remember that fish live in structured environments. They must learn where shelter lies, where food appears, and which areas are risky. A bowl or tank can make them seem simple because it gives them little to do. In richer settings, their abilities become clearer. A goldfish navigating a maze is not just swimming randomly. It is using memory to reduce uncertainty. Months later, that pattern may still guide its movement. The animal many people underestimate is carrying a stronger sense of the past than folklore allows. Salmon remember the smell of their birthplace after years at sea. A salmon begins life in fresh water, then travels to the ocean, where it may grow for years across vast distances. When it is time to reproduce, it finds its way back toward the stream where it hatched. Smell plays a central role in this astonishing return. Young salmon imprint on the chemical signature of their home waters, creating a memory that survives the ocean years. Later, as adults, they follow scent gradients back through rivers and tributaries with remarkable precision. Other cues may help during the ocean phase, but the final approach depends strongly on that remembered water. The journey can be exhausting and dangerous, yet the drive to return is powerful. A stream is not just a place on a map. For the salmon, it is a chemical memory formed at the beginning of life. The fish returns to the origin of its own body, guided by scent through a changing world. Mantis shrimp judge rivals before choosing whether to fight. A mantis shrimp is armed with one of the fastest strikes in the animal kingdom, but using that weapon against another mantis shrimp can be risky. Before escalating, individuals often assess each other. They may display their bodies, show their striking appendages, or exchange signals that reveal size and strength. This is intelligent because a fight can injure both opponents. If a rival is clearly stronger, backing down may be the better choice. If the contest seems winnable, aggression may increase. Some species also compete for burrows, which are valuable shelters. The decision is not simply attack or flee. It is a judgment made under pressure. Mantis shrimp are also famous for extraordinary vision, with eyes able to detect kinds of light humans cannot see. Their world is rich with signals. In a confrontation, color, posture, and movement become information. The animal that could strike like a hammer often thinks before it swings. Crabs can learn to avoid danger in laboratory mazes. A crab moving sideways across a tank may seem guided only by reflex, but experiments show that crabs can learn from frightening experiences. In maze studies, shore crabs have learned to choose routes that avoid areas associated with unpleasant shocks or threats. Over repeated trials, they improve their choices and remember safer paths. This matters because it shows flexible learning in animals with nervous systems very different from ours. In the wild, a crab must navigate rocks, tides, predators, shelter, and food. A mistake can be costly, so memory has clear survival value. The laboratory maze simplifies the world, but the lesson is real. The crab can connect a place with danger and alter its future movement. It is not merely a shell with legs. It is an animal gathering information, updating behavior, and choosing a safer path through space. Even near the edge of a tide pool, learning is at work. Lobsters remember social defeats and change their behavior afterward. A lobster fight can decide more than a single moment. When two rivals meet, they size each other up, display their claws, and may escalate into a contest of strength. The winner often becomes more confident in later encounters. The loser may become more cautious and less willing to challenge another opponent. This shift is not just a temporary mood. It is linked to changes in the animal's nervous system, including chemicals that affect posture, aggression, and readiness to fight. In the lobster's world, remembering defeat can prevent injury. A creature that backs away after losing may survive to feed, grow, and try again another day. This is a form of social learning written into the body. The animal carries the result of an encounter forward into its future choices. Beneath the hard shell, experience is changing behavior. Even on the seafloor, memory can shape confidence. Hermit crabs compare shell quality before deciding to move. For a hermit crab, a shell is not decoration. It is a portable home, a shield, and a matter of survival. When a new shell appears, the crab does not always rush inside. It may inspect the opening, feel the weight, and compare the fit against the shell it already has. If the new one is too small or too heavy, moving could be dangerous. If it is better, the crab must transfer its vulnerable body quickly. Some hermit crabs even gather around empty shells in size order, forming vacancy chains where one crab's move creates an opportunity for another. This behavior shows decision-making under pressure. The crab must judge value, risk, and timing. A poor choice can leave it exposed. A good choice can improve growth and safety. In this small shoreline drama, intelligence appears as careful comparison, one shell at a time. Bees can count landmarks during flights to hidden food. A bee traveling across a landscape does not simply drift toward flowers. It can use features along the route as a kind of measured guide. In experiments, bees trained to find food after passing a certain number of visual markers often searched in the expected place, even when spacing changed. That suggests they were not relying only on distance. They were also tracking the number of landmarks passed. This ability is useful for a forager that must return to a precise location in a busy environment. A meadow is full of movement, color, and scent, yet a bee must remember where success was found. Counting landmarks gives another tool for navigation. The brain doing this is tiny, but the task is large. The bee flies through a world of patterns, turning repeated signs into a route. Its journey is not random. It is guided by memory and number. Ant colonies solve traffic problems without any leader directing them. A trail of ants can look like a living road, full of workers moving in both directions without collapsing into confusion. No overseer stands above them. Instead, each ant follows simple local rules. It responds to scent trails, touches from other ants, and obstacles in the path. When a route becomes crowded, traffic patterns can shift. When food is found, chemical signals strengthen the path toward it. Over time, the colony can settle on efficient routes that no individual ant designed alone. This is one of the clearest examples of collective intelligence. The single ant has limited information, but the group creates a solution through constant feedback. Engineers and computer scientists study these patterns because they reveal how complex systems can organize themselves. A line of ants crossing a pavement may seem ordinary, Look closer, and it becomes a lesson in distributed problem solving. Leafcutter ants assign different jobs according to body size. In a leafcutter colony, workers are not all built for the same role. Some are large enough to cut and carry heavy leaf fragments. Others are smaller and tend the fungal garden inside the nest. The tiniest may ride on carried leaves, helping defend against parasites that could harm the workers. This division of labor is one reason the colony can function with such precision. Body size becomes part of the colony's organization. Each worker follows tasks suited to its shape and strength, and together they create a system more capable than any single ant. The leaves moving along the trail are only the visible part of a much larger operation. Beneath the surface, farming, cleaning, defense, and care must all be coordinated. No ant understands the entire society. Yet the colony acts like a living machine, built from thousands of specialized bodies. Honeybees can learn faces using patterns like tiny portraits. A honeybee does not see the world as humans do, but it can still learn a face-like pattern. In experiments, bees have been trained to choose images resembling human faces by associating them with a reward. They use arrangements of features, such as the relative placement of shapes, rather than recognizing identity in the human sense. Even so, the ability is astonishing. A bee's brain has fewer than 1 million neurons, yet it can process visual patterns well enough to solve a task that seems far beyond its size. In nature, this kind of pattern learning may help bees identify flowers, landmarks, or nest entrances. The face experiment is powerful because it takes a familiar human image and shows how a tiny animal can extract structure from it. A bee hovering near a blossom is not just drawn to color. It is a skilled reader of visual order. Bumblebees can roll balls for rewards in experiments. In a laboratory arena, a bumblebee can learn to move a small ball into a target area to receive sugar water. At first, the task seems completely unnatural. Flowers do not require ball rolling, yet bees can watch a demonstration, explore the object, and eventually complete the action themselves. Some even choose the nearest ball when given options, which shows they are not merely copying a fixed movement. They understand enough of the goal to make the task easier. This is fascinating because it reveals flexibility beyond normal foraging. The bee takes an object that has no natural meaning and turns it into part of a learned solution. Such experiments show how animals can apply general learning skills to new problems. The reward matters, but so does the route to get there. In a tiny body, curiosity and memory combine into a small act of invention. Cockroaches can learn timing and remember safe places. Cockroaches are often treated as pests, but their survival depends on quick learning. In experiments, they can associate certain cues with safety or danger, and they can learn when conditions are better for feeding or hiding. Timing matters because these insects are most active when risk is lower. They respond to light, smell, touch, and the memory of past experiences. A cockroach that finds a reliable shelter can return to it. One that learns a threat can avoid repeating the same mistake. Their nervous systems are compact, but they are remarkably effective. They can squeeze through narrow spaces, navigate cluttered environments, and make fast choices when exposed. Their intelligence is not charming in the way people often prefer, but it is extremely practical. To survive alongside humans for centuries, they have had to become expert readers of opportunity. A cockroach's mind is built for persistence. Turtles can learn touchscreen tasks and remember them later. A turtle may seem slow in body, but its learning can be surprisingly steady. In research settings, some turtles have been trained to use touchscreens, choosing shapes or colors in exchange for food. They can learn which image leads to a reward, and some remember the task after long delays. This challenges the old idea that reptiles are simple, rigid animals. A turtle's world rewards patience and memory. It must remember basking sites, feeding areas, shelter, and seasonal routes. A touchscreen is artificial, but it reveals abilities that make sense in natural life. The animal sees a pattern, makes a choice, and learns from the outcome. Its pace may be calm, yet the mind is active. Reptile intelligence often appears without drama. It is measured, durable, and easy to underestimate. A turtle choosing an image with its beak is showing that slow does not mean simple. Crocodiles cooperate in hunts more often than people expect. A crocodile is usually imagined as a solitary ambush predator, waiting in still water. Yet observations suggest that these reptiles can sometimes coordinate during hunts. Several individuals may position themselves around schools of fish, or larger animals may drive prey toward waiting companions. They do not cooperate like wolves or dolphins, but their behavior can be more flexible than old stereotypes suggest. Timing and placement matter. A crocodile that moves too soon may ruin the chance for others. One that holds position can help trap prey in a dangerous zone. These animals also show social behaviors around nesting, basking, and territory. Their brains are not mammalian, but they are capable of learning and responding to complex situations. The surprise comes from expectation. We see a prehistoric shape and assume a primitive mind. Then the animal acts with patience, strategy, and awareness of others nearby. Monitor lizards can solve feeding puzzles with surprising flexibility. Monitor lizards are active hunters with sharp senses and strong curiosity. In captivity and experiments, some have learned to open doors, work latches, or solve containers to reach food. They often investigate with tongue flicks, claws, and repeated adjustments. What makes them impressive is their persistence paired with flexibility. If one approach fails, a monitor may try another angle rather than simply repeating the same action. In the wild, this matters because prey can hide in burrows, crevices, nests, and vegetation. A lizard that can explore a problem creatively gains more chances to feed. Some monitors also have large home ranges and may remember profitable locations. Their intelligence is physical, practical, and direct. There is no need to make it seem human. A monitor facing a food puzzle shows a reptile mind working in its own way, testing the world through movement until the hidden reward becomes reachable. Snakes learn from experience when hunting difficult prey. A snake strike can look automatic, but hunting is shaped by learning. When prey is hard to capture or risky to handle, experience matters. Some snakes improve their approach after repeated encounters, adjusting timing, angle, or persistence. They can also learn which prey odors are worth following and which situations may lead to trouble. Young snakes are born with many instincts, yet their future success depends on refining them. A mouse that escapes, a frog that kicks free, or a defensive prey animal can all teach a lesson. The snake's nervous system records outcomes and changes future behavior. This is especially important for animals that may go long periods between meals. Each chance matters. A snake does not need limbs or facial expression to show intelligence. Its learning appears in subtle adjustments, in the pause before a strike, and in the choice to follow one scent instead of another. Frogs adjust their calls when noisy environments interfere. A calling frog is trying to be heard. In a pond filled with other voices, wind, rain, or human noise, that can be difficult. Some frogs respond by changing their calls. They may call louder, shift timing, or adjust pitch so their signal stands out. This is a form of communication intelligence shaped by competition. A male's call can attract a mate, but only if it reaches the right ears. Calling also carries risk because predators may listen too. The frog must balance effort, danger, and effectiveness. In cities or near roads, some species alter their behavior in response to the constant background sound humans create. That makes their calls small experiments in adaptation. A frog at night is not simply repeating a fixed note. It is responding to the acoustic world around it. The sound that reaches us from the water may be a carefully adjusted signal. Elephants comfort distressed companions with touch and soft sounds. When one elephant becomes upset, others may approach, touch it with their trunks, or produce low, reassuring sounds. These responses suggest a deep sensitivity to emotional states within the group. Elephants live in societies where bonds can last for many years, and comfort helps maintain those relationships. A distressed individual may be reacting to a threat, separation, or social tension. The companions around it do not remain indifferent. They gather, make contact, and sometimes place trunks near the mouth or face. These gestures are intimate in elephant life because the trunk is both a sensory organ and a tool of social connection. Comforting behavior reveals that intelligence is not only about solving puzzles. It is also about noticing another's state and responding in a way that reduces distress. In a herd, the mind is relational. Survival is supported by memory, attention, and care moving from one body to another. Elephants remember distant water sources during long, dry seasons. In dry landscapes, memory can mean survival. Older elephants may lead their families across great distances to water that has not been visited for months or even years. These routes are not guessed at random. They are built from long experience of rainfall, terrain, and seasonal change. The knowledge held by a matriarch can help an entire group survive drought. This is why elder animals are so important. They carry information gathered across decades, including where to go when familiar places fail. Young elephants learn by following, and the group's future depends on that transfer of knowledge. A dry riverbed may look empty to a human visitor, but an experienced elephant may know where to dig or where to travel next. Memory becomes a map written across a lifetime. In harsh country, intelligence is not speed or clever tricks. It is the ability to remember water when the land has forgotten it. Elephants can distinguish human languages linked to different risks. Elephants living near people may learn that not all humans pose the same level of danger. In experiments using recorded voices, wild elephants reacted differently to languages or speech patterns associated with groups that varied in threat. They also responded to cues such as age and sex in human voices. This shows fine social discrimination across species. The elephants were not simply hearing people and fleeing. They were sorting information. Who is speaking? What kind of person might this be? How risky is the situation? Such judgment is valuable in landscapes shared with humans. Running every time wastes energy, but ignoring danger can be deadly. Elephants must make careful choices based on limited information. Their hearing is excellent, and their memories are strong. A few spoken words carried on the air can become a warning, a clue, or something safe enough to ignore. That is intelligence shaped by coexistence. Giraffes may use quiet social knowledge to maintain friendships. Giraffes were once thought to have loose and simple social lives, but research has revealed more structure than many expected. Individuals can form lasting associations, especially among females, and these relationships may influence where they travel and with whom they spend time. A giraffe's social world is spread across large spaces, so maintaining bonds requires recognition and memory. There may be no dramatic display to announce a friendship. Instead, The evidence appears in repeated companionship, shared movement, and tolerance at feeding sites. This kind of intelligence is easy to overlook because giraffes are calm and often silent. Yet social knowledge does not need to be noisy to matter. Knowing which individuals are familiar can reduce stress and help with group living. A giraffe crossing open ground may seem alone from a distance. Look longer, and it may be part of a subtle network of remembered companions. Hyenas understand social rank and alliance better than expected. A spotted hyena clan can be socially complex, with ranks passed through maternal lines and alliances that shape daily life. Each individual must know who holds power, who is related, and who may support whom during conflict. Their famous calls and gatherings are part of this social world, but the real intelligence lies in tracking relationships over time. A hyena may decide whether to challenge, retreat, or recruit help depending on the identities present. This requires memory and judgment. The old image of hyenas as simple scavengers misses almost everything important. They are skilled hunters, attentive group members, and sharp social strategists. Females often dominate, and rank affects access to food and opportunity. A clan is not a mob. It is a shifting political system, and survival depends on reading it correctly. In the night, a hyena's whoop may carry across the plain, but its mind is listening for status. Lions coordinate hunts through spacing, timing, and patience. A lion hunt can unfold slowly, with each individual's position affecting the outcome. Some lions move wide around prey while others hold back. One may begin the pressure that causes the herd to shift toward hidden companions. Success depends on timing rather than speed alone. Lions are powerful, but many prey animals are faster over distance. Cooperation improves the odds, especially in open country where cover is limited. Not every hunt is perfectly planned, and lions do not always cooperate equally. Still, experienced hunters can take on roles that fit the situation. The intelligence is in reading movement, waiting for the right moment, and responding to the group's pattern. A hunt may fail many times before one succeeds. That makes patience essential. The image of a lion charging is only the final moment. Before it comes a long calculation of distance, wind, attention, and opportunity shared across the pride. Raccoons remember puzzle solutions long after learning them. Raccoons became famous in early animal intelligence studies because they could open complicated locks and remember solutions after long delays. Their hands are sensitive, and they explore objects with remarkable skill. A latch, lid, or container becomes something to test from every side. Once a raccoon discovers a working sequence, it may retain that knowledge and apply it again later. This makes sense for an animal that thrives in changing environments. Raccoons feed on many things, live near water, climb well, and often succeed around human buildings. Their intelligence is practical and opportunistic. They do not need a single specialized trick because their world changes constantly. Memory turns one successful night's discovery into a future advantage. A raccoon at a bin or stream is not merely rummaging. It is investigating. Its paws gather information, its mind keeps the useful parts, and the next obstacle becomes slightly easier. Squirrels pretend to hide food when thieves are nearby. A squirrel storing food is vulnerable to eavesdroppers. Other animals may watch and steal from its caches later. To reduce that risk, some squirrels make deceptive movements that look like hiding food while keeping the item in their mouth. This false caching can mislead observers and protect the real store. The behavior is fascinating because it shows how competition can sharpen strategy. The squirrel must notice that it is being watched, change its behavior, and create a misleading cue. It is a small drama of secrecy, played out in parks, forests, and backyards. Food stored today may be needed weeks later, so protecting it matters. The animal's memory is already working hard to track real hiding places. Add thieves, and the task becomes social as well as spatial. A squirrel patting soil with empty paws may look comic, but the performance may be a clever act of misdirection. Dolphins can recognize themselves on screens and in mirrors. When dolphins encounter reflective surfaces, some show behavior suggesting they understand the image relates to their own bodies. In studies, individuals have inspected marks placed on them by positioning themselves to see the affected area. They have also used mirrors in ways that resemble self-directed checking rather than social reaction. Video screens add another layer because the animal must connect a moving image with itself through a different medium. This is difficult to test and interpret, but the results are compelling. Dolphins rely heavily on sound in the wild, yet they can process visual self-information in artificial settings. That flexibility is part of what makes their minds so intriguing. Self-recognition does not mean they think exactly as humans do. It suggests they can treat their own body as an object of attention. A dolphin turning before a mirror is not just seeing motion. It may be asking, in its own way, "What am I looking at?" Whales may teach songs that spread like ocean-wide trends. Male humpback whales produce long, structured songs that can change over time. In some regions, a new version of a song spreads from one population to another, moving across vast stretches of ocean. The pattern resembles a cultural trend, with whales adopting and modifying what others are singing. This is extraordinary, because the singers may be separated by enormous distances, yet the sound tradition still travels. The songs are not random noise. They have repeated themes and phrases, and groups can shift together as the pattern changes. Scientists study these changes to understand learning at a scale far beyond human classrooms. A song can rise in one area, spread through neighboring whales, and replace an older version. The ocean becomes a living broadcast network. A whale singing in deep water is not only expressing its own presence, it may be carrying the latest version of a shared tradition. Birds can migrate using star patterns learned when young. For some migratory birds, the night sky is part of navigation. Young birds learn the rotation of star patterns around the northern sky, and that information helps them orient during migration. Experiments in planetariums have shown that changing the displayed stars can alter the direction birds try to travel. This is astonishing because it means the sky itself becomes a map through experience. The birds are not reading constellations as humans name them. They are learning the reliable center of rotation and using it as a guide. Migration already demands extraordinary endurance, timing, and sensory integration. A bird may also use magnetic cues, sunlight, smell, and landmarks, but the stars can provide a stable compass on clear nights. A small bird lifting into darkness carries knowledge gained earlier in life. Above it, the sky turns. Within it, a learned pattern points the way. Crows drop nuts into traffic to crack them open. In some cities, crows have learned to use cars as moving nutcrackers. A bird drops a hard nut onto a road and waits for a vehicle to run over it. Then it retrieves the broken pieces when the moment is safe. Some have even been observed using pedestrian crossings, taking advantage of traffic pauses. This behavior reveals flexibility in an environment built by humans. The crow is not frightened into helplessness by roads and machines. It studies them as forces that can be used. The hard shell is the problem. The weight of a car becomes the solution. Timing is crucial because the reward lies in a dangerous place. Urban animals often face new challenges, and crows are among the best at turning those challenges into opportunities. A city street may look entirely human, but a crow can reinterpret it as a tool. Octopuses can change hunting strategies after one successful attempt. An octopus hunting in a reef or rocky den must solve problems with a body unlike any land animal's. It can probe crevices, pounce under a web of arms, or flush prey from hiding with jets of water. When one tactic works, it may use that approach again under similar conditions. If prey escapes, it can change method. This flexibility is important because prey animals hide in many different ways. A crab under a rock does not require the same approach as a shrimp in open water. The octopus explores through touch, taste, sight, and movement all at once. Its arms gather information while the central brain guides the larger plan. A successful hunt becomes a lesson stored for later. What looks like fluid improvisation is also learning in action. The animal adjusts to the situation, turning its soft body into a shifting toolkit. Parrots sometimes invent names for their favorite human companions. Some parrots create distinctive contact calls for individuals they know well. In the wild, parrots use contact calls to keep track of flock members, and captive birds may adapt that ability to their human household. A bird might produce a particular sound when seeking one person and a different one for another. This is not the same as using human names in our language, but it reveals social labeling through sound. Parrots are vocal learners, meaning they can acquire and modify calls through experience. That gives them a flexible way to maintain bonds. A favored person becomes part of the bird's social world, and the bird may shape a sound around that relationship. The idea is charming, but it is also scientifically meaningful. It shows that vocal intelligence is rooted in social life. A parrot calling from its perch may be doing more than making noise. It may be addressing someone specific. Dogs can smell emotional changes linked to human stress. A stressed human body changes in subtle chemical ways. Breath and sweat can carry different compounds when a person is anxious, and dogs are sensitive enough to detect some of those changes. In studies, trained dogs have distinguished samples taken from people before and after stressful tasks. This ability helps explain why dogs sometimes seem to know when something is wrong before we say anything. They are not reading minds. They are reading scent, posture, movement, and routine with extraordinary attention. Smell is central to a dog's world. Where humans see a room, a dog also smells its recent history. Emotional change leaves traces in that invisible landscape. For working dogs, such sensitivity can be trained for support roles. For companions, it can deepen the bond at home. A dog resting nearby may notice shifts that even the person experiencing them has not fully recognized yet. Animal minds reveal intelligence shaped by survival, not human standards. The most important lesson from animal cognition may be humility. A creature can be brilliant without speaking, building machines, or solving human puzzles. Intelligence grows from need. A migratory animal must know direction. A social animal must know companions. A hunter must understand timing. A prey animal must detect danger before it arrives. Each life creates its own mental challenges, and evolution shapes minds to meet them. This is why a test designed for one species may fail another unfairly. Hands, eyes, noses, wings, shells, and fins all change what a problem means. A puzzle box may impress us, but in the wild, intelligence may appear as patience, memory, caution, or cooperation. The animal world is not a ranking chart with one winner. It is a vast collection of solutions. Once we stop asking which creature is most like us, we begin to see how many kinds of cleverness exist. Every intelligent creature shows a different way to understand the world. A bat hears space. A bee reads flowers. A salmon remembers water. A dog follows scent as if it were a story. None of these experiences is identical to ours, yet each is a real way of knowing. The study of animal intelligence invites us to step outside the human center of things. It shows that awareness can be tuned to sounds we miss, colors we cannot see, and signals we never notice. Every species lives inside its own sensory world, and its mind grows around that world. This does not make other animals lesser. It makes them different. Their intelligence may be quiet, quick, social, physical, or deeply tied to place. The more science learns, the more life feels populated by many kinds of perception. To watch an animal closely is to glimpse another version of reality. The world is not understood in one way. It is understood through countless living minds. And so, we come to the end of our journey through the hidden brilliance of animal minds. Tonight we have seen intelligence appear in many forms. In a bird solving a puzzle with patient attention. In an ocean creature learning through touch. In a herd remembering the way to water. In a small insect reading patterns that seem far too large for its tiny brain. Again and again, the living world has shown us that thought does not belong to one shape of body. It can move through wings, paws, fins, trunks, claws, and antennae. It can appear as memory, trust, planning, play, or care. It can live in a call across the sea, a tool held in the hand, or a path remembered beneath the stars. Perhaps that is the most comforting part of all. The world around us is not empty or automatic. It is full of noticing, full of choices, full of lives quietly learning how to survive. So as we leave these remarkable creatures behind for now, let your own mind begin to soften. Let the facts drift away like tracks fading in sand. Let your shoulders loosen. Let your breathing find its own calm rhythm. There is nothing more you need to solve tonight. If you enjoyed this gentle journey, you're welcome to like, subscribe, or leave a thought below. It helps other sleepy souls find their way here too. And if you happen to still be awake, another quiet exploration is waiting for you on the screen. But for now, let the animal world grow still in your imagination. Let the forest settle. Let the ocean darken. Let the night gather softly around you. Sleep well, and good night.